work in a lab attached to mine. And some of you I don't know, but I'm Amber Harris-Gozer, and I'm a neuroscientist on campus, and I'm going to talk to you about sensation and physiology today. Let's start with biological foundation. Some of you have taken that class with me online. Yes, raise your hand. Okay, currently enrolled. Oh, it's so nice to see you to your face. I love it. Okay, so the brain chapter that I'm going to talk to you about comes from Nova Project, which is an online open source text chapter that you can utilize so you don't have to purchase anything to be able to study this. And that's linked here. There are 4 lobes of the brain. Anybody want to tell me what they are?
Frontal lobe.
Frontal lobe. What else? Occipital. What else? Parietal and temporal. Okay, so those are depicted here, with this part being the front of the brain. You've also got the cerebellum, which is arguably large enough to be its own lobe, although it's not recognized as such. That's located in the base of your brain and processes movement. So just be aware of what the lobes of the brain are. You're not going to have to answer very extensive and in-depth questions on a major field test about the brain. There are general questions about the brain on there. There's not too many of them, so don't kill yourself studying that part. Just be aware of major things. So there's a study sheet that's available from Mayfield Clinic, which is really nice. I'm actually going to pull this one up so I can show you how you can utilize that best. There's an additional study sheet there as well. You're going to want to know just a basic overview of what takes place in different areas of the brain. So you don't need to know this fossa information right here. You probably won't need to know this information right here. But you can look and note that there is a right and left side of the brain. There are 2 different hemispheres which are divided and connected by a clump of axonal dense tissue, which is called corpus callosum, right? It's connected to 2 hemispheres there. Okay, those are the lobes of the brain. Okay. This is the part that I want you to pay attention to on this study tool to study for the major field achievement test. These are the deep structures. You've got the hypothalamus, and you can see where that's located at, pituitary gland, pineal gland, and the thalamus. So the hypothalamus is involved in regulatory processing, so sleep, hunger, thirst, body temperature. The thalamus acts like a relay station. He's sort of like the guy that's on top of the Navy ships in the vest with the light sticks showing the planes where to land and stuff, right? So he routes everything that's in the brain. I would know about the limbic system. Just know that that runs through the middle of the brain and contains the reward processing areas. You don't have to know about all of the areas in the limbic system. You wouldn't have to say, well, the limbic system includes the nucleus accumbens and the ventral tegmental area and all that jazz. Just know that the limbic system runs through the midbrain and processes reward, which you probably heard at some point. So that's one really good study guide that you can utilize, and that's what I would take out of that. Questions so far? Okay. So I made a cheat sheet list for you as well for some of the important areas. Additionally, you can know that the amygdala is involved in emotional responses. Prefrontal cortex is the link between decision making and emotion. If you will remember Phineas Gage, who you've undoubtedly heard about at some point, you can remember that his accident caused damage in the ventromedial prefrontal cortex, and you remember how his behavior went a little wonky. So just remember decision-making and emotion related to the frontal area. Cerebellum for movement, thalamus, I already talked to you about, and reticular formation in the base of your brain, and that manages cortical alertness. I feel confident that if you know these parts, then that will be what you need to know about the areas of the brain. Here's a picture that you can study so you kind of have a general idea of where it's at. You're never going to label a picture on that test, I don't think, and so you won't have to study this figure and know it by heart, but you can draw it for fun and impress your friends. That's always a good time. Questions about the brain? Okay, let's talk about the nervous system. We have the peripheral nervous system, peripheral meaning on the outside portions of your body, which is divided into the somatic nervous system and the autonomic nervous system. The autonomic nervous system is particularly important for psychologists because it contains the sympathetic nervous system and the parasympathetic nervous system. Anybody remember what the sympathetic nervous system does? Yes.
It raises the alertness and prepares you for fight or flight.
Perfect. That is a perfect answer. So it prepares us for fight or flight. So it is activated whenever we experience stress, whenever we experience enhanced alertness. So on the African savanna, if you were running from a lion, that would be taking place. If you're getting ready to take the major field achievement test, it might be taking place, right? So we activate it in our current context as well with stressors. But the system can't engage in that much physiological overload in the long term. It would be very deleterious for our health. So we have the parasympathetic nervous system, which is a compensatory system that brings everything back to homeostasis. So it undoes what the sympathetic nervous system does as a rule of thumb. So that's really helpful. What takes place in that situation is we get more blood flow to the periphery, to the muscles, so that if we have to run away, we can do that. We have things like digestion slow down because let's say a rabid bear came in this room and we all needed to get away from that bear. We would need to expend our energy in fighting the bear or moving away from the bear, so there's no time for digestion. Likewise, ovulation slows down. It's not time to ovulate. We're trying to get away from this bear, right? So you can imagine that the overall motives inside of the physiological system are changed and are reflected by the sympathetic nervous system activity. I put a lot of fun pictures in here for you guys. A lot of these pictures come from the second edition of the King book for Intro to Psych. That looks like a little bit like that orange book, yes. Which is probably in its third edition now, right?
This is in the 8th edition.
Oh, okay.
No, 4th edition.
Okay.
Sorry, 8th edition is my abnormal psych.
I got so old and no one told me. Okay, yeah, all right, so that's good. So there's still good pictures, but they may not be exactly like the ones that are in there. So, but that's where they come from, so I can give credit to that author. Also from the NOVA project, you can see how the different parts of the brain fit into the central nervous system, and you don't have to have that memorized, but it's something that can help you conceptualize the moving parts and pieces while you're studying. Also in the nervous system, we have different kinds of cells. Most of the cells that you have in your brain are glial cells, but no one talks about them because they're not as cool as neurons. So we're going to focus on neurons that get all the love. Neurons signal using action potentials and a variety of other cellular activities which most people don't talk about. Action potentials are electrical and they travel across the neuron, like you've probably learned before. And these neurons don't touch each other. There's a space in between neurons which we call the synapse, right? You've heard synapse, okay. So electricity diffuses in liquid. And so we would not be able to use electricity to communicate from cell to cell because in that extracellular space where the synapse is, that electricity would diffuse. So we use neurotransmitters in that physical space to communicate. So neurons communicate using electricity and chemicals, which are those neurotransmitters that you've heard of. Who can name some neurotransmitters? Yes.
Serotonin?
Love it. What else we got? Yes.
Norepinephrine.
Norepinephrine. Very nice. What else? Dopamine, acetylcholine, oxytocin can act as a neurotransmitter. So there's quite a few of those. The ones that are most popular that you might be confronted with at some point are dopamine and serotonin because of their role in mental health and what we know about mental health. Okay, so these neurotransmitters leave the sending cell and they bind to the receiving cell on receptors. Those receptors are like a lock and key. Each receptor fits a certain kind of neurotransmitter, sometimes two different kinds of neurotransmitters. And so just be aware that that's a lock and key system. Let's be reminded of how the action potential works because it's exciting. It's an all or nothing process, right? You can't have small action potentials or really large action potentials. You either get one or you don't get one. And so the process is rather consistent from cell to cell. I put a video here for you to watch of the action potential. While you're learning about these sensation and physiology items, you might find that some of them can be hard to remember. They may have details that are difficult to remember. You may just struggle in general because sometimes reading them in words are difficult. So look up pictures on the internet and look up videos, and that really helps people to understand what that looks like while it's actually going on in the system. So here is a sample video for you, but we'll talk about the parts and roles of the action potential. This is a sending neuron, and this is a receiving neuron. The reason that this picture has blanks in it is because you can use it as a study tool. After we've talked about the parts of the neuron, you can see if you really know them by plugging in the answers to those questions. So on this sending neuron that we have here, what do you think this part is?
The cell.
It's the nucleus, right? It's the center of the cell, it's kind of the powerhouse of the cell. So that's what this one is. What are these little branch areas on the outside ring? Dendrites, right? These are these tree-like branch structures that receive incoming information and stimuli from nearby cells. And so this information is stimulating the cell, and then the cell becomes active. What's this long area here? Not the covering, but the stick-like structure.
Axon.
It's an axon. Perfect. The action potential is propagated down the axon in a sweeping-like fashion. What's the covering on this? Myelin sheath. Love it, right? It's a fatty-like substance that insulates that axon. Think about what happens when a wire is insulated. It transmits information a lot better, right? It's protected. Myelin serves both of those purposes for the axon, and so myelin is very important. So this action potential is activated by stimulation. It's sweeping down the axon, and it comes out down here to these terminal buds, or terminal buttons, yes, or even boutons, depending on where you're at in the world if you want to be fancy with it. Okay, so the electricity is traveling down this axon out to the terminal buttons, but remember that the electricity can't get across that gap because there's fluid and goop in there and it's liquid. So we need chemicals to do that. Synaptic vesicles are hanging out at each of these terminal buds just waiting for that electrical stimulation, and when it comes in, they release neurotransmitters into the synaptic cleft. And from there, those neurotransmitters bind to the receiving cell, to those receptors, and then it stimulates that process to begin all over again, and we have action potentials at the next cell. Okay, so how does the action potential actually begin, you ask? Yes? Okay. So what takes place with all of these parts is contingent upon something that we call membrane potential. On the outside of the cell, there's a barrier between the cell and the extracellular space. And there's a difference in electrical charge between the inside of the cell and the outside of the cell. Inside the cell, the natural resting state is negative 70 millivolts on average. So inside the cell is always negative in its resting state. Outside the cell is positive. When the cell is stimulated by some kind of incoming activity, that membrane between the inside of the cell and the outside of the cell becomes permeable. So ions can flow in and out. Ions are negatively or positively charged particles that are floating around in that space. So when that membrane becomes permeable, sodium comes in. What's the charge of sodium? It's positive. So inside the cell moves from a negative 70 millivolt state to a more positive state. If and when it reaches somewhere around negative 55 millivolts, it's enough to trigger the action potential. You recall that I said the action potential is all or nothing, right? So it has to hit that negative 55 millivolts threshold. That's called the threshold of excitation, okay? So that's what starts the action potential, and it sweeps down that axon. So the cell cannot stay in a constant state of propagating action potentials, and we cannot see a depolarization that stays for any long period of time. In fact, that process occurs in 10,000ths of a millisecond, so faster than you even snapping, right? So it's very, very fast. The cell returns to its negative internal state by a process called repolarization. All that sodium has come into the cell, but the sodium can't get back out. It's actually too fat to go through typical out-channeling mechanisms. So the cell sends positively charged potassium outside of the cell to make it more negative on the inside again. Okay, so sodium in and potassium out. Sodium in, the cell gets more positive. Potassium out, the cell makes itself more negative again. Got it? Okay, could you stand up right now and tell everybody in the room how the action potential works? That's how you know what you really know, right? Okay, so you're like, I think I have this. But when you're studying, if you will look and see if you think you can teach it to someone else, you'll become more critical of what you think that you know. You'll challenge yourself in a different way. So think about it that way while we're studying for the test. Questions about the action potential. Did I scare you, Lindsay? I'm not going to call on anyone. Okay. Endocrine system. The nervous system is not the only thing that we need to survive. I'm kind of biased and I would like it that way, but we have other things going on. The endocrine system is one of them, and hormones are part of that system. I've provided another resource for you to look at if you want to refer to that. Just know that hormones are chemical messengers. They're released from hormonal glands or endocrine glands in our nervous system. Can anybody name an endocrine gland? Yes.
An endocrine gland.
Yes. Something that secretes hormones. Yes. Pituitary. Good. Pineal.
Yeah.
Mm-hmm. Yep. Good. So you already know that there are several different glands that are there. So there's a chart on the next slide which I'm going to show you. And I'm going to list some of the hormones that are primary signalers for the endocrine system and the nervous system. Luteinizing hormone is not on the list, but it's one that you might come across. So I want to add that to the table. This is released by the pituitary gland, which Kristen mentioned, which was awesome. Okay. We have steroid hormones, and hormones are classified as either steroid or peptides and proteins, and that's just a dichotomization based on what they're made of. So these are made of steroids, these are made of peptides and proteins. I don't think you have to go into that in great depth. Steroid hormones include things like cortisol, estradiol, and testosterone. You've probably heard at least of testosterone. Males and females both have testosterone, but we typically think of this as the male hormone, right? Because that's what provides males with secondary sex characteristics. Cortisol is known as the stress hormone. Those of you that took my classes before recall watching videos of Robert Sapolsky blow-darting baboons in Africa, and that was all because he wanted to get their blood samples so he could look and see how much cortisol was in their system. There are a variety of studies that are done looking at stress hormones in humans and non-human primates. Oxytocin is known as the signaler of love. Oxytocin is special because it functions as a neurotransmitter and as a hormone. So that's just a little fun fact. We also have prolactin, thyroxine, and vasopressin. Vasopressin is associated with monogamy in mammals, which is kind of exciting too. So questions about a general overview of hormones. It's exciting, right?
So quiet today.
Yeah. So that was Biological Foundations of Behavior, a crash course in the nervous system with focus on neuron signaling and endocrine system. But let's talk about psychopharmacology. Many of you are taking that class. Yes? I know I've had at least 3 of you. What's going on today? Okay, so how the drugs work. It's very exciting. There's a game called Mouse Party. Let's see if the link works. Okay. Mouse Party is something that can be used to study neural mechanisms at the synaptic level of drugs. Hypothetically, you're a mouse and you're at this party and all of the mice are on drugs. Okay. Okay, I'm going to show you one so you'll know how to use it as a study tool. We're not going to do them all. You're going to pick a mouse that's on some kind of drug, and you can make a guess on what drug that they're on by their behavior. So does anybody want to pick one of these mice that we can use as an example?
Dancing with.
Okay, that's the one that everybody always picks. What do you think that this mouse is taking?
Who said that? No drug.
Ecstasy. Yes.
Serotonin transporters are responsible for removing serotonin molecules from the synaptic cleft after they have done their job.
Okay, so this is actually the sending cell and the receiving cell, and so you're looking at the synaptic mechanism for this drug at this time. So after they explain what takes place, you can click next.
Ecstasy mimics serotonin and is taken up by serotonin transporters. In fact, ecstasy is more readily taken up than serotonin itself.
This is really nice because it lets you go on your own pace. So until you have that portion of the mechanism conceptualized correctly, you can wait before you click the next button, which is nice.
This interaction with ecstasy alters the transporter. The transporter becomes temporarily confused and starts to do its job in reverse. The transporter starts transporting serotonin out of the cell. The excess serotonin becomes trapped in the synaptic cleft. As a result, it binds again and again to the receptors, overstimulating the cell. Ecstasy affects serotonin pathways responsible for mood, sleep, perception, and appetite. Ecstasy also indirectly interacts with the reward pathway. The excess serotonin stimulates a milder release of dopamine along the reward pathway, giving ecstasy slightly addictive properties.
So at the end, ultimately, it'll zoom out and give you a whole brain picture, and then it'll tell you what's going on at the systemic level with that drug, what the behavioral and cognitive effects are that are important. So it puts it back in the party. So there's cocaine, LSD, alcohol, methamphetamine, marijuana, heroin. So although using drugs isn't funny, you can make it fun to learn about drugs using Mouse Party, and it's a good study tool. Okay, so we also have to consider things that are drugs that are not just illicit drugs or things that we consider to be inherently bad. We have to think about prescription drugs. And in psychopharmacology, you remember there's no distinguishing between those two in the system. So we have to think about antidepressants. The different classes of antidepressants are what I think you need to know about antidepressants for the test. There are tricyclics, monoamine oxidase inhibitors, selective serotonin reuptake inhibitors, and selective norepinephrine reuptake inhibitors, and atypical antidepressants. So I would familiarize yourself at a basic level by just knowing what those different classes are of the antidepressants. For drug use and addiction, it's important to know about tolerance and dependence. Anybody want to tell me what tolerance is? Yes.
Tolerance is a buildup of resistance to a drug, and you need a higher dosage to
Good.
get the same effect.
Good. And dependence. Andrea.
Okay, dependence would be where you're physiologically or psychologically you need the medication. And it's different than addiction.
Good.
It's you've created that issue, I guess, by building tolerance.
Good. I like that you distinguish between needing something or wanting something, and I like that you distinguish between if something is physiological or psychological. So that is a thing. So years ago, even in recent years, psychological dependence wasn't recognized by as many psychologists as it is now. So now we know that that's important. Good. Neurotransmitters mediate this drug process, and all of the drug processes really. And I've made a list of important neurotransmitters pertaining to psychopharmacology and their action on different receptors. There's a book chapter for you there too, which is actually very short, but it summarizes these. So we have acetylcholine. Acetylcholine plays a role in learning and memory, Alzheimer's disease. Have you heard about Botox injections? Okay, that works through acetylcholinergic system processing. If you are unfortunately attacked by a black widow spider and you have muscle spasms, that's because of acetylcholine. Poison blow darts, which I hope never happens to anybody, also activate the ACH system. Dopamine is involved in reward circuits, motor circuits, and Parkinson's disease, schizophrenia, and other mental health situations. Norepinephrine is involved in arousal and depression. Serotonin, also involved in depression. It's abbreviated as 5-HT, so if you come across that, it's 5-hydroxytryptamine. It's the structure of that molecule. It's involved in aggression and schizophrenia. Glutamate is an excitatory neurotransmitter, which is involved in anxiety, learning, and being able to memorize large amounts of information. So you're probably utilizing glutamate right now, and it's exciting, and it's an excitatory neurotransmitter. GABA is gamma-aminobutyric acid. It's involved in anxiety as well, epilepsy, and it's an inhibitory neurotransmitter. So glutamate is an excitatory neurotransmitter, and GABA is an inhibitory neurotransmitter. Okay. And endogenous opioids are involved in pain, analgesia, and reward. If you've heard about runner's high, that works through endogenous opioids in the system. Questions about any of these neurotransmitters? Does it sound familiar? Oh, good. Lots of head nods. I love it. You ready to talk about sensation and perception? What's the difference between sensation and perception?
Sensation is a signal to your brain of outside input. Perception is how you view or receive that information.
Perfect.
And how you interpret it.
Perfect. So all the time we have signals coming in from the periphery or coming in from our eyeballs or our mouth or our smeller, and it's all coming into the system. But things like actually perceiving smell or actually perceiving pain are all mediated by the brain. So you may recall hearing me say at some point, if you've had my class, if there's no brain, there's no pain. Okay? Pain doesn't actually exist in the nervous system if there's no brain to process it. So I'll use pain as an example. Pretend that this is an oven, and I just put my hand on it, and the oven is hot. So signals come up through receptors in my hand, and they travel through nerves in the periphery, and they get to my spinal cord. It's not pain yet. It's nociception still, because it's just neural signaling that's taking place. It'll travel up through my spinal cord to the thalamus. It's not pain yet. It's still nociception. When those signals get to the mid part of the brain, they're signaled out into other parts of the brain that are involved in the perception of pain, such as the anterior cingulate cortex. When I have a perceptual experience or a perceptual phenomenon, and I think, that hurts, that's unpleasant, I'm having this reaction to it, I know where it's located at that point it becomes pain. So pain is the perceptual piece, nociception is the sensation. Make sense? So sensation,
How does shock work then? Because like I was in a car wreck a few months ago, and
Yeah.
my whole knee, like from like mid thigh all the way down to mid calf, was like obliterated, and I didn't feel it until like 3 hours later.
Yeah, that is called episodic analgesia. So 37% of people that go to the ER for any kind of peripheral trauma experience episodic analgesia. So they don't have pain immediately, but then later there's an onset of pain. That is mediated by the endogenous opioid system, by the sympathetic nervous system mechanisms, which are poorly understood, and by the insular cortex in the brain and the anterior cingulate cortex. It is an adaptive survival mechanism that allows us some grace for handling what's taking place. And I'm not going to go on a whole pain lecture, but I just want to tell you one more thing because I'm excited. Okay. Henry Beecher did work with soldiers in the Civil War and found that even though some of them had lost a limb, they weren't experiencing any pain. They were experiencing depression for what their future might look like for having lost a limb. And I'm not sure if depression is the right word in today's context, but that's what Henry Beecher described it as. But what was ironic is that they were using needles to administer some low-grade analgesic pain-relieving drugs. And when they would do that, the soldier that had lost a limb and didn't feel any pain from losing a limb would complain about the needle stick. So the thing about episodic analgesia is that it's isolated to the area of injury, which is a really strange phenomenon. Yes?
So the sensation of pain is still happening, but the perception of it is been distorted?
Perfect.
Or...
Yep.
Okay.
It's a perfect example for the difference between sensation and perception. I'm glad you asked. Okay, take my pain class. We'll have a good time. Okay, so that's sensation. So we're receiving stimulus energies from the external environment. We're taking in information. Perception is when we organize and interpret that or make meaning out of it. I want to give you one more example before we move past sensation and perception. You might have heard the question before, if a tree falls in the woods and there's no one there to hear it, does it still make a sound? What are your thoughts about that question? Andrea?
It creates sound waves, but until there's a recipient for the sound waves to create a perception of sound, I guess, then there's no sound. It's just...
Yeah, so that's the neuro answer, which makes me really happy. So a neuroscientist would say that there's not a sound because sound is something that is perceived, and that there has to be an ear there to change the information from sound waves into something that is perceived as sound. So it depends on maybe what bucket you're working out of, what field you're working out of, but that's what a neuro person would say because they are interested in the difference between sensation and perception. All the while, information is coming into the system, and it's contingent upon thresholds for whether or not we can process that information or not. If you've ever had a dog whistle, you know that you can make sounds at high enough frequencies that dogs can hear that we don't process. When I first started teaching, I was over in the Howell building about 10 years ago, and my students had a text message ringer that they could hear, but other people couldn't hear. And because with age, we lose some of our hearing processes. And I was just a little bit older than them at that time, but it wasn't enough, and I couldn't hear it. And so their phones are going crazy. I heard nothing. So kids can have ringers that we can't hear. So just be aware of that if you have children.
Which is annoying anyway. I never liked that ringtone.
Oh,
Just that high pitched one.
oh yeah. Interesting. Yep.
Can I ask a question?
Yes.
So this may be this may be sort of just outside of the scope of this. But I've been looking a lot of the news, and I've been really interested in the sonic attacks on the diplomats in Cuba, right? And so, have you all heard about this? Okay, so we had these American diplomats in Cuba, and they all started coming home with all of these symptoms, right? Like mild traumatic brain injury, nausea. There were some other things that were associated. So then they started investigating, and they discover that they were the victims of a sonic attack that they didn't hear, but they experienced the effects of.
Yeah.
And I'm just wondering, so you don't have the perception, but there's a lot that's associated with the sensation, sort of outside of the realm of our awareness.
Isn't that bizarre?
Yes, and terrifying.
And terrifying.
Yeah.
Yeah, I think that's such a good example. I'm so glad that you said something about that. I don't know much about how that works exactly in the brain, but it's hard to figure out where perception starts. So they didn't perceive it in the beginning, so nobody was debilitated and said, we're obviously undergoing a sonic attack. There was a period of confusion, but then they started to exhibit these signs and symptoms, and at that point they are perceiving something, but it's delayed perception. So that's perception that's not in reaction to incoming stimulation in the environment. So it's hard to say. It's really interesting. I hope a lot of people don't figure out how to do that.
I know, right?
It's a bad deal. Okay. External stimulation can make its way into the nervous system because we have specialized receptors to pick up that information. I just realized I never took my hand off of the hot oven. Take it off now. Okay, but let's say that I put it back on just for a second. There are receptors in my hand that can pick up that information. So for example, in your hand right now, you have 3 kinds of receptors. You've got mechanoreceptors, which respond to mechanical stimulation. If you touch your desk with your fingertips and you feel something, that's mechanical stimulation. You have chemical receptors that are there. So if I were to pour acetone on my hand felt really cold, that would be processed by chemical receptors. And you also have temperature receptors, hot and cold receptors. So for putting my hand on this oven, it would be the high threshold temperature receptors, thermal receptors as we call them, that pick up that intense heat that would allow me to pull my hand off, right? So there are different kinds of sensory receptors. Our sensory receptors allow us to pick up that information. If something is wrong with my thermal receptors and I've got my hand on the oven, I may not pick up that information. That flesh is just burning and I don't pick up that information. So we're very reliant on this specialized receptor system all throughout the body. And they work differently depending on where they are in the body. If you've been so unfortunate that you've had a kidney stone, you know that a buildup of renal calculi in the ureter tube that connects the kidney to the bladder is lined with high threshold mechanoreceptors that are responding to stretch. So those kidney stones are about 2 sizes bigger than the diameter of that ureter, and so that activates those high threshold mechanoreceptors. Okay, we're good. Specialized cells. They transmit sensory information to the spinal cord and ultimately to the brain so that we can process this special information about what's coming in. And depending on what receptors are sending the signal and what they're sending, the information is routed to different areas of the brain. So pain is processed in a different area of the brain than hearing or smell. So that's distributed differently amongst the brain lobes in their respective areas. This is just a pretty picture of all the different receptors that exist for sensory receptors. You can look at vision, hearing, touch, smell, and taste. They're specialized according to what type of information that they receive and how they have to transmit that. We could spend several days talking about sensation, and I could tell you what an eyeball looks like, how it works, how it signals information to the brain, and then we could do the ear, and then we could do taste, and then we could do pain, but nobody wants that in their life right now. So I'm just going to tell you about vision as an example of the way that you should look at sensation and perception for any one sense, and then you can do the other ones on your own time. I've given you access to those materials as well, but that book is a really awesome book for sensation and perception. If you will read that chapter, you'll be taken care of. But let's talk about vision. Folks at McGill have a brain from top to bottom activity that shows you the different parts of the eyeball. It's kind of exciting what that looks like, how it works. So that's a good thing to know. Okay. This also is another picture of the parts of the eyeball. Okay, so you can see the outer portion of the eye is the cornea. You hear someone say they've got a scratch cornea, it's because it's on the outside of the eyeball and it has a lot of protection from the external environment, but we have to keep it lubricated and we have to keep it protected, and that's why we've got those blinkers, which are really helpful. So we've got the iris, which is this part of the eyeball, which is behind the cornea. You can't typically see it, but it stretches or has a little bit more give to it than most things do, and then it comes back together depending on how much light is coming in. You can feel this experience if you move from a room that's really, really bright to one that's really, really dark. You can feel your vision changing, and that's that stretching that's taking place there. The lens bends the light or processes the light, and that light comes through the eyeball and projects onto the back portion of the eye. And on the back portion of your eyeball here, all along this part, you have cells that are specialized to receive that light that's coming in, and that's how we can process what we see. If you're colorblind, it's because you have different cells in the back of your eye compared to other individuals. This is the optic nerve. The eyeball is connected to the brain. And some ophthalmologists would argue that the eyeball is a mini brain. I don't know, we can duke it out at another time. But it is directly connected to the brain. So that is this optic nerve. Because this optic nerve is connected to the brain, this part right here, where that nerve is, does not have those specialized cells. That's why you have a blind spot. You have a blind spot in your field of vision right now, but you can't see it, right? Nobody has a big black circle at the bottom right part of their eye or anything right now. If you do, you might want to get it checked out. Perception fills in the gaps, okay? It's not really there in the back of your eyeball. It's not really projecting that information, but our brain uses perception to fill in that gap. It's kind of wild. There are different exercises that you can do on the internet to locate where your blind spot is at in your field of vision. So if you don't yet believe me, you will come to believe me by participating in these very fun Friday night type of activities that you do with your friends. These specialized receptors that are located in the back of your eyeball are called rods and cones. And so here's another glorious picture of the eyeball that you can study. So lovely. These rods and cones are different. The rods are sensitive to dim light, but don't do much for us to perceive color. And they work well in low illumination. And we have about 120 million estimated number of rods in our eyeballs. We also have cones, which are located predominantly in the fovea, and they respond more to color. So that's the difference between those two. They work best under high illumination, and we have about 6 million of them. So we have significantly less cones than we do rods. Okay? That's why if an individual is colorblind or they can't process things or their cones are different, they can still see and function typically because we have all of these rods that are processing the other characteristics of light and what's being projected into the system. That is a flashcard of rods and cones that you can check out. Okay, so like I said, I'm not going to go through all of the different ones, but you can see this module for hearing here, which is a nice 3-chapter. This is how the ear works. Okay, and you can impress your friends with the if a tree falls in a forest question and blow their minds, or make them very angry, which is also possible. There's a picture of the ear and its parts. I wouldn't worry about learning all of the parts for each sensation. What I would learn is the mechanism inside of that system that transmits the sensory information to the brain so that it can later be perceived. So in the eyeball, it's the rods and cones that are the sensory receptors that are taking in that information and sending it to the brain. In the ear, it's in this region right here that the mechanical stimulation comes in. As Andrew said, there are vibrations in the ear. That is processed in the ear and sent on to the brain. We have an auditory nerve, which is analogous to the optical nerve that connects the eyeball to the brain. The auditory nerve connects these hearing apparatus to the brain. Other senses include taste and smell, touch and pain, which is my favorite, and the vestibular system. Okay. A pep talk for sensation and physiology for the MFT. If you get confused when you're reading it, read it again. If you're still confused, utilize YouTube so that you can see a picture or a video of whatever the mechanism is. 2-Minute Neuroscience is the bomb.com. This guy explains complex neurophysiological mechanisms in 2 minutes or less. He's got an action potential video, he's got membrane potential videos, all kinds of things. He's a good resource. He knows what he's talking about. He's legit. So I would utilize that resource. Synaptic mechanisms of drugs can be studied best using Mouse Party. The primary illicit drugs that you would need to know about related to neurotransmitters would be on Mouse Party. You don't have to know all the drugs. I think if you have a good idea about what the major neurotransmitters are, how they work in the synapse, you'll be doing pretty good. I would pay special attention to dopamine and serotonin if you can. What is the other name for serotonin? 5-HT. Love it, Danielle. Good. Okay. Utilize your textbooks from previous classes. If you still have them, don't panic. Your friends might have them and you can share. But Carlson's Biological Foundations of Behavior class book is really helpful. The King book is good, which I think you have, and that's really nice. Psychopharmacology book, which is orange in the 2nd edition by Meyer and Klinzer, is also helpful for drugs, for studying drugs. So textbooks from previous classes. Most of the book chapters that I took out of Nova are encapsulated within this link, which is a free online psychology textbook. Okay, and seriously, utilize your friend or someone that's a human that can help you, because you might be studying and you say, I know this, I really know this, but then you get in front of the test and you're like, well, I thought I knew this, right? You can get in the middle of that situation by testing yourself differently before the test. If I were to ask some of you if you felt really good about something, you might say, yeah, I think I know that. But then if I said, get up here and tell the rest of the class about it, you might question what you really know. Part of that is self-doubt, but part of that is a critical lens inside of your mind that's really looking at what you know and don't know. I'm not suggesting that you go out and teach classes about all these things, but if you will get a friend and say, I think I know this, let me explain it to you, you'll find where the holes are, and that's a good tool to be able to use. So please provide that support to each other, or locate someone who's got a lot of friends that will still love them after this great information is put upon them. I like to call my mom. I've been calling my mom and explaining neural mechanisms for 10 years. Sometimes I think she puts the phone down and mops the floor. It's okay. It's really just so that I can understand what I know and what I don't know. Okay. Focus on recall and not recognition. When you want to know if you know something about these mechanisms, don't just look at it and say, oh yeah, I recognize that. Okay, what you want to do is see if you can recall it. So utilize tools like that action potential sending and receiving cell tool that has the words blanked out. See if you can recall them on your own and fill them in. Okay, so that's one way you can test your knowledge for this type of material. Questions about that? Okay, I've shown some of you this before, and I want to just end on a musical note. See what I did there? Okay, and it's about the brain, and there's going to be some famous neuroscience people and science mediators that are in this video that you might recognize.
It's amazing to consider that I'm holding in my hands the place where someone once felt, thought, understand what this unappealing object is all about. What the object is all about.
Here is this massive jelly you hold in the palm of your hand, and it can contemplate the vastness of interstellar space. Contemplate the vast brain has evolved from the inside out. Its structure reflects all the stages through which it has passed.
Information in the form of energy streams in simultaneously through all of our sensory systems in the form of energy. And then it explodes into this enormous collage. What this present moment looks like, what it feels like, and what it sounds like. It explodes into this enormous collage. And in this moment, we are perfect, we're whole, and we're beautiful.
It appears rather gruesome, wrinkled like a walnut, and with the consistency of mushroom. Mushrooms, like a walnut.
What we know is included in cells called neurons, and there are something like 100 trillion neural connections. This intricate and marvelous network of neurons has been called an enchanted loom. An enchanted loom. The neurons store sounds to snatches of music, whole orchestras playing inside our heads. 20 million volumes worth of information is inside the heads of every one of us. The brain is a very big place. In a very small space.
Information in the form of energy streams in simultaneously through all of our sensory systems in the form of energy. And then it explodes into this enormous collage. What this present moment looks like, what it feels like, and what it sounds like.
No longer at the mercy of the reptile brain, we can change ourselves. Think of the possibilities. Think of your brain as a newspaper. Think of all the information that gets stored, but it doesn't take up too much room because it's full. Think of all the information that gets stored. We see with the eyes, but we see with the flame as well. And seeing with the flame is difficult imagination. The brain can contemplate the masters. The brain is evolved in successive stages.
And then it explodes into this enormous collage. And in this moment, we are perfect, we're whole, and we are beautiful.
It is the most mysterious part of the human body, and yet it dominates the way we live our adult lives. It is the brain.
Okay, so learning with music is also fun. There's some really good brain facts in there. Jill Bolt Taylor is the person who's saying that stimulation comes in from the external environment as sensation, and then it explodes in our brain into a collage, and that's what allows perception. That's a good TED Talk to watch if you're interested in sensation and perception. She's a neuroscientist who experienced a stroke, and then she does a TED Talk about the stroke that she experienced. So that's a sensation and perception talk. Oliver Sacks is also in the video, and he says we see with the eyes, but we see with the brain as well. I think he's referencing cortical blindness. You can be blind because your eyeballs don't work, but you can be blind because the part of your brain that processes vision doesn't work. So remember that it's a multi-step system, right? So that can also help you to understand sensation and perception as well. Thoughts about the video?
I've seen that TED Talk that you're talking about, Karen. This is really good.
Yeah, it's good stuff. Okay, that's all I have. Everybody's really quiet. I built in time for questions. Yes.
Okay, I have, so since we have a little bit of time,
Let's
I'm
do it.
wondering if you wouldn't mind talking about the decision points that went from you being an undergrad student
Okay.
to you being a neuroscientist. So what were the decision points? Like what were the things that changed your trajectory? Or if they maybe you had never changed your trajectory, what supported your path from undergrad to neuroscientist?
Okay. I think when I was an undergrad in the beginning, if you had a time machine and you went back and you said, you're going to be Dr. Bozer and you're going to be a neuroscientist, I'd just laugh in your face. If I had $1 million at that time, I would put it on that not being what I do. So I was not someone who always aspired to be a neuroscientist. It just kind of happened. So when I was in undergrad school, I was interested in psychology, and I thought I was interested in working in mental health. And I found out at that time that's not really where I needed to be. But I was inherently interested in the nervous system because of some experiences that my family had had. But I didn't know that's what I wanted to do for a job. So around my junior, senior year, I became aware of what neuroscience is. I don't think I knew a thing about it prior to that. And then I realized that you could use neuroscience to study some of these things, like chronic pain, for example. And then my senior year, I got involved with university things. And I got involved in Psych Club, the Psych High Honor Society. Prior to that, I was not involved on campus very much in wholesome activities. So I started engaging in wholesome activities. That was a good thing for me. All of these opportunities started coming about. I developed relationships with faculty. One of the students in Psych High had a dad that worked at UT Arlington and ran a research lab there. So Psych High was going to go up there for the day. I'm like, okay. So we went up there. When I went into the lab, I saw that they were doing research on the chronic pain disease that my dad had. And I realized that you could contribute to the world that way. And so I was like, I want to do this. I want to come to PhD school. But I wasn't ready. I had a decent GPA. I graduated at the top of my class in 3 years, but I had very little volunteer work, no research experience. I couldn't get into a PhD program. So I stayed here and I got a master's degree in a master's program that we don't still have. We have a new one now, which is similar. And during that time, I got research experience. Dr. Newby was my thesis chair. I did a study in that room right there, collected some data, and I presented it with a poster at a conference, and then I got into PhD school. All the while during my master's program, I was talking to that man at UTA about how to get into the program, if I could volunteer in the lab. And ultimately, I got into his lab with people that came from Ivy League schools, but he knew who I was. And we had built a relationship, and he knew I was interested, and I was around. So I was always reminding him that I was going to be hopefully coming there eventually. So I went there. I worked in his lab for 3 years and got a master's degree in neuroscience and behavioral neuroscience. I kept going, and I went to work right across the hall on my dissertation with his best friend in electrophysiology. And then I came back here as faculty. So that was really my path to neuroscience. I guess you could say my path to neuroscience started just based on the family that I was born into, but it was not realized until I was like a senior as an undergrad that that's what I was going to do. I was better at other things. I'm still probably better at other things, but I picked something that I'd like to do, and it's made a lot of difference. So on Labor Day, for example, my husband was working, and I just woke up and I was like, I'm going to go to the lab. So I came over here and went to the lab and worked all day, and someone's like, hey, you're crazy, it's your day off. But if you find something that you love to do, it's not like working. It's not the same as working. Don't get me wrong, we work really hard, but loving it sure takes the edge off. So as an undergrad, you have an opportunity that you may not have again. That opportunity is to get involved in things, get involved in clubs, volunteering, working different kinds of jobs in the field, and then if you don't like it, you can finish up the project you're working on and you can move on and try something different. There are very little consequences for that. But if you wait until you graduate and you don't get involved in things and then you take your first job and you don't like it, you found out that's not for you, there are more consequences at that time in your life. So you have a lot of opportunities on campus, clubs that you can be involved in, research you can be involved in. Some of you are involved in research. That's awesome. And that helps you to find out who you are and where you're going and what your next step in the future is. But it also builds relationships with people who can open doors for you. I wouldn't be able to have the job that I had if I hadn't developed relationships with faculty that gave me opportunities. And so that happens when we know people, when we see that people want to work.
Do you work closely with the research program that's happening in Waco with the VA CERT? Because they have a neuroscience portions there, and Waco's students were kind of lacking in that region. Baylor took up all the positions in those spots, and most of the Waco students did the other research areas except for the neuroscience.
Yeah, it's a good question. I haven't worked with the program before. I actually just became aware of the program about a month ago. And the department head is like, okay, we'll make a day for you to go down there. So I'm going to go down there and see what I can do to help. But at this point, I don't have that relationship built. My relationships are in the Metroplex with TCU, UT Southwestern, UT Arlington, University of North Texas, and University of Texas at Dallas. I did my PhD at UT Arlington and developed relationships at that time, so that's where my strengths are. But yeah, hopefully we'll do some things with Waco. They have brain imaging techniques that I haven't utilized. I have 6 years of research experience in animal research, basic neuroscience and electrophysiology, and experimental neurosurgery, and that's really where my strength is. But a year ago, I started an EEG lab on the second floor of this building, and so that's a new thing that I'm doing. I believe that down there they have access to an fMRI machine and stuff, which I wouldn't know how to use, but maybe I'll learn.
I think that's important too, right? Because I think there's this idea that we come out of our graduate programs fully baked and ready to attack any kind of problem that we could have, and that's just not true,
So
right?
not true.
Because what my experience is and what you're saying too, and I think this is true for all of us, is that this is a lifelong learning process, right? There is not a point at which you're going to be like, yep, got it. There's a phenomenon called imposter syndrome. Have you heard of imposter syndrome?
Yeah.
Imposter syndrome is you feel like at some point everybody's going to realize that you're a fraud and that you don't know nearly as much as you think you know. And it's true for all people. You get into this profession, you're like, at some point somebody's going to start laughing at me saying, you don't deserve to be a faculty member. You don't deserve to have a license to practice psychology. You can't do neurosurgery. And here we are, all feeling like imposters, doing the thing that we are not 100% sure we can do.
Yeah.
Real.
That is real.
That is real.
All day, every day.
Yeah.
And so the best thing that you can do if you want to get into a field in academia is to find people that are going to build you up. That support is really good. And we have that here, which is why we're all really excited about being at Tarleton. But when you don't have that, some people can really struggle.
Yeah.
So I left a position in cellular electrophysiology and experimental neurosurgery to come here. And we don't have surgeries going on in the math building or invasive cellular electrophysiology. But I wanted to come here. This was the right place for me. These are the right people. These are the right students. It's the right environment. So sometimes you're like, well, we have to make it work. What's a neuroscience thing that I could do here? Well, we could write a grant, get an EEG. That's neuroscience. Never ran an EEG, never touched an EEG, but you have faith in your background. You're like, okay, I'm trained as a neuroscientist. I did the school. We'll figure it out. And oftentimes in laboratories, we're just figuring it out. But everybody is. Everybody has equipment malfunctions. Everybody has training that needs to take place and stuff like that. And that's all fine.
Yeah. Sometimes actually doing the thing is what prepares you to do the thing.
Yeah.
Right? you are pushed into this role. It's like, it's like Harry Potter, right? He didn't feel like a hero. He just did what he needed to do, and then he was. That's really sort of what it's like.
It really is, and I'll just tell you a story from my own personal experience. That was kind of a victory, but also a little bit sad. So when I went into my PhD program, like I said, there were quite a few people that came from Ivy League schools and stuff, and a lot of people were like, where's Tarleton even at? What is that? So they used to call me special ed. They didn't think I was as smart as them. Someone got a hold of my GRE score, and that's what I faced the first year of my PhD program. There were 90 of us. On the day that I graduated, 5.5 years later, there were 4 of us sitting in the graduation chair. It's not the GPA you come in with. It's not the school you come with. It is an exercise in frustration tolerance. It is about persistence. It's about resilience and dedication. And so in undergrad school, we emphasize the GPA. Here's what's going to happen when you apply to grad school, because I've been on a variety of teams that look at and review students for money and for entrance into PhD programs up in the Metroplex that are very competitive. What typically happens is people sit around a table, faculty sit around a table, and they bring in all of the paper applications, because a lot of us still like paper. So you submit it digitally, but we print it. So we put it around the table, and we pull out the people that have really bad GPAs, like 2.0, 2.5, trash. Don't even look at it, right? Okay. Everybody else on the table has a good GPA. Everybody does. 3.8, 3.9, 3.7, 4.0. What takes place at that point is faculty start saying, I know Andrea. She's been volunteering in the lab. I know she does good work. I'll pull it out. Or I know Chris Bowman. I've seen her present at a conference, and etc. So we're human too, and the people that we hire are people that we know. And so don't just submit an application to grad school and say, I've got a 4.0 GPA, right? You need an application that has something on it. You worked a job, you did volunteering, you did something, and you need to know somebody there. Let them know you're interested. It's okay to call somebody or email them and say, I'm really interested in your research about dreams, and I think I might want to work on that, and I'm going to apply to the PhD program. Can I drive down there and see you? Can I have lunch with your grad students? Can I have a tour of the lab? It's completely terrifying, but if you do that, they'll know who you are, and you'll be more likely to get in. So that's something that's very, very helpful, is building those personal relationships. If you don't know where to start, you can come by one of our offices. We may know somebody who does what you're interested in or can help you find that person.
Any other thoughts, questions? This is your one opportunity to ask a question of an actual neuroscientist.
I just want to share this with people really quick. It's a graduate study book in psychology, and it's really, really, really good. And it shows like pretty much every requirement that you'd need to get into all these grad schools. And it's pretty much like every single one in the States.
Hey, Stephen, do you mind passing it around?
Yeah, absolutely.
We don't have a ton
And
of
I
time,
can, or y'all take down like the ISBN number or whatever if you want to, and because it's been really, really helpful.
It's organized by section. So let's say you want to study developmental psychology. You can look up all the schools that have grad programs in developmental psychology. And then like he said, it tells you what you need to know to get in. It'll tell you, I think, even how much the application is, what the average GRE scores are for acceptance, what you need to do to get that done. So it's one-stop shop.
It shows how many students like have applied and how many finished from the most recent graduating class too, kind of like you.
Yeah.
Bragging about to a degree, which is pretty cool.
Yeah.
In the neuroscience field, especially when it comes to the perception part, has it reached a point where the science has started to approach philosophical questions about perception?
Neurophilosophy is a field. I've never worked in it, but you know, when you get a group of us together at a conference and we go out and have a drink, we all turn into neurophilosophers. So it's more of a hobby for most of us, but it's a field for some people. I have a neurophilosophy book you can have if you want it. You just come to my office. Andrea.
Okay, any advice for grad school when you're geographically locked in place?
Mm-hmm.
So maybe the field that you're most interested in, there's really no schools that specialize in it in the area that you absolutely are not allowed to leave.
Yeah, so then you have to pick a different field. Academia is about moving. You have to move to find a special program that you want to do. And when you get out with your PhD, if you do a postdoc, you're going to move again. I know lots of people that live separate from their spouse doing postdocs, so moving is a thing, and it's a challenge. But if grad school is still the dream, maybe you could find a closely related field. They're rare for good reason, but maybe you could find a faculty member that would let you have a little creative liberty and work on something that you liked as long as it was relatively similar to what they're doing. So I wouldn't give up, but just be prepared to make some compromise if that's the case.
I think if I get to the PhD level, I think I've already made the pact with my husband that tough, we've moved where you needed to go.
Yeah.
If I get to that level, where I'm accepted, then
And
you
it's
come with
hard.
me, but
Yeah.
But it can be done. I lived apart from my husband for a year
no,
Yeah.
when I was doing my
He would
predoctoral
survive.
internship. Huh?
he would survive.
There, opposites.
No, no,
Yeah.
he wouldn't survive,
Yeah.
which is okay.
Yeah.
Which is okay. I'll just take him with me. He works for a global company, so I'm sure he can find.
Sure.
You talking made me more stressed and less stressed all at the same
Yeah.
time.
Okay. Sometimes it has an effect on people. I don't know.
I don't
what
think
to
it's
say.
you. I think it's like the information provided. I was like,
Uh-huh.
okay, that makes sense. Like
Yeah.
we've already spoken to some grad school people. It's just it's like, oh man, application
Yeah.
to do. Like,
Give you some scary information, but then comfort you about it. Yeah, that's how I roll. So if you come to my office, if you have questions about biological foundations or psychopharm or anything sensation and perception related before you take the test, you can come to my office to talk about grad school. I love all things grad school. I went 3 times. I did it for 10 years. There's not a mistake I haven't made. And also, we have a master's in applied psych program if you'd like to do a PhD later. It would be really great for you to stay here and do some research with us for a couple more years and really strengthen your application. We'd love to have you. At this time, we're just actively recruiting, so come on in. Let me know, and we'll get you set up. Okay? Okay. See you later. Thank you. Yep.